Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Methods for Scientists and Engineers by K. Shankar Rao. We will continue to discuss topics from Module 2, Numerical Methods in Physics. In today's class, let's discuss how to find roots of an algebraic equation numerically. So an equation f of x equal to 0 is called an algebraic equation if f of x is a polynomial function. For example, x cubed minus 3x squared plus 5x plus 9 equal to 0. This is an algebraic equation. On the other hand, if f of x contains trigonometric, exponential or logarithmic functions, then it is known as a transcendental equation. For example, 3x squared plus e to the power x sine x plus log x minus 3. This is an example of a transcendental equation. Now, what is the meaning of root of an equation? The value of x for which f of x equal to 0 is known as the root of the equation. And we already know that if the algebraic equation is quadratic or cubic, there are some ready-made formulas for the solution. For example, if you take a generic quadratic equation ax squared plus bx plus c equal to 0, we know the standard form of the solution, right? X equal to minus b plus or minus b square minus 4ac divided by 2a. So we have this kind of a luxury only in the case of quadratic or cubic function, but if you have a polynomial function of higher degree or a transcendental function, then this kind of a ready-made solution is not available. In such cases, we will have to resort to a numerical iteration method like bisection method or Newton-Raphson method to find the solution. So in today's class, let's discuss about Newton-Raphson method, which is used for numerically arriving at the solution of an algebraic equation. So we have a function f of x. We need to find the value of x for which f of x equal to 0. So let's assume that x1 is the exact solution to this equation. So let me say, for example, when x equal to 3, f of x equal to 0. So x is the exact solution, x1 is the exact solution. But I do not know the value of x1, so I start with an initial guess. Let x0 be my initial guess. Say if if 3 is the exact value of the solution, I will start with an initial guess 2.5. Now the trick here is that your initial guess should be close to the exact solution. So if I write x1 equal to x0 plus h, the difference h should be very, very small. Only then this method will work with good accuracy. So once again, x1 is the exact solution at which I need to arrive, and x0 is the initial guess. So starting from x0, you need to finally arrive at x1. That's our aim. And we are already familiar with Taylor theorem, so which says that you can write the value of function at x1 in terms of the value of function at x0. Right? So I write f of x1, which is equal to f of x0 plus h as f of x0 plus x1 minus x0 into f prime of x0 plus x1 minus x0 square by 2 factorial f double prime of x0 all the way to infinity, where f prime is the first derivative, f double prime is the second derivative, etc. Now from this equation, you can note x1 minus x0 is h. So I can rewrite the Taylor series in terms of the step size h as f of x1 equal to f of x0 plus h into f prime of x0 plus h square by 2 factorial f double prime of x0 all the way to infinity. This is equal to 0. As I said, if your initial guess is good, then x0 and x1 are closely spaced, which means the value of h is very, very small. So from this series expansion, h square, h cube, etc., they are going to be much smaller compared to h, right? So you can neglect all these higher order terms and worry only about the first two terms. So my Taylor series gets simplified as f of x naught plus h into f prime of x naught equal to 0. From this, when I rearrange the terms, I can write h equal to minus f of x naught divided by f prime of x naught. So remember the equation x1 equal to x naught plus h. Now you substitute for h, so you get x1 equal to x naught minus f of x naught divided by f prime of x naught. So I said x1 is the exact solution and x naught is the initial guess. Now, even if x1 is not the exact solution, if you do this kind of an iteration, you will find that x1 is a much better approximation compared to your initial guess x0. So basically you are starting with an initial guess and improving upon it. And if you are not happy about the accuracy of x1, you can repeat the iteration once more. So you get a newer approximation x2, which will be x1 minus f of x1 divided by f prime of x1. And x2 will be a much better approximation compared to x1 and x0. If you are still not happy, go ahead and find x3, which is equal to x2 minus f of x2 divided by f prime of x2. So you keep doing that until you reach the desired accuracy level. So in general, xn plus 1 can be written as xn minus f of xn divided by f prime of xn. This is known as Newton-Raphson formula. Now physically, what is going on here? So I can explain this graphically. So you take a function f of x. So on the x-axis I have x, on the y-axis I have f of x, and this curve is your f of x function. So you can see at this point the value of f of x equal to 0. So this is the exact solution at which you need to arrive. So you start with an initial guess xi. So this is your xi, and you find the corresponding point on the function f of xy. And what you do, you find the slope at this point. Okay, so the slope is f prime of xi, right? Now slope is a straight line. You plot that straight line, and the point where the slope intersects the x-axis, this is your new approximation or your better approximation. So xi is your initial guess, xi plus 1 is the new approximation. Now geometrically what happens here, if you call this angle as alpha, then tan alpha equal to AB by AC, and tan alpha is nothing but the slope at this point, right? And slope is the derivative, so f prime of xi equal to, what is AB? This point is f of xi, this point is 0, so AB is f of xi. And what is AC? Point A is xi, point C is xi plus 1, so AC is xi minus xi plus 1. So f prime of xi equal to f of xi divided by xi minus xi plus 1. So you can interchange these two terms and you rearrange, you get xi plus 1 equal to xi minus f of xi divided by f prime of xi. This is your Newton-Raphson formula. So if you want to see it in an iterative mode, so this is what you are doing. So you have some function for which you need to find the exact solution. So from this graph, you can note this is the exact solution, the exact root. Now you start with an initial guess x0, and what you do, you find the corresponding point on the graph f of x0, then you find the slope f prime of x0, then you look at the point where the slope intersects the x-axis, that is your new approximation x1. Once again, you find the corresponding point on the function f of x1, find the slope f prime of x1, look at the point where the slope intersects the x-axis, that is your new approximation x2. So you keep repeating it. So you can see that this is your initial guess. In each iteration you are moving closer and closer to your exact solution. So after a number of iteration you will arrive at the exact solution. But one thing to remember, these are numerical solutions, not analytical solutions. So even after infinite iteration, you may not reach the exact solution, but you will reach a value which is very, very close to the exact solution. So which is good enough for you. So one thing you can note from this graph is that if your initial guess is very good, if it is very close to your exact solution, then you will require a less number of iterations. For example, instead of x0, if your initial guess was x2, you would take less number of iterations to reach this point. On the other hand, if your initial guess was somewhere here, it will take more number of iterations. So when you are performing numerical methods manually using paper and pen, the choice of the initial guess is important because you cannot spend so much time on iterations, right? On the other hand, if you're performing this using a computer, then it doesn't matter whether your initial guess is here, here or here, because computers have very high processing speed, gigahertz of processing speed, so they can perform a large number of iterations within 1 second itself. Okay, so whether your initial guess is here or here, your computer is going to take pretty much the same time, or even if there is a difference in time, it is so small that you will not be able to notice it. Let's do a quick problem. Using Newton-Raphson method, find square root of 7. Now this doesn't exactly look like an algebraic equation, right? So let's first write it in the standard form. So let's call square root of 7 is x, or x square equal to 7, right? So this is an equation. Now you bring 7 to the left hand side, x square minus 7 equal to 0. So this looks like a standard algebraic equation, right? So this is your f of x. Now you need to find f prime of x, the derivative of f. Derivative of x square minus 7 is 2x. Okay. Now you need to start with an initial guess. Okay. So in this kind of problem, using a calculator, you can find what is the exact solution is, right? So just type it in your calculator, you will get square root of 7 is something like 2.645751, something like that. Okay. So you can choose your initial guess something close to that value. So let me say 2.5 is my initial guess. It doesn't matter whether you choose 3 or 2, you will still be able to arrive at the actual solution after a number of iterations. Okay. So the idea is that you start, especially when you are doing it manually, you start with an initial guess which is closer to the actual value. So my initial guess x0 is 2.5. And let me cross check. So I find out f of x0, f of 2.5, this is minus 0.75. So I need to make sure that f of x0 is not equal to 0, right? If it is equal to 0, that is your exact solution. Your initial guess is the exact solution. And there is no point in doing this iteration, right? Okay. Now I need to improve upon my initial guess. So I find x1, which is x0 minus f of x0 divided by f prime of x0. x0 is 2.5 minus f of x0. This is f of x. So you substitute for x as 2.5. So 2.5 square minus 7, which is minus 0.75 divided by f prime of x0. This is f prime of x. Substitute for x, 2 into 2.5, 5. So when you do this, you get x1 equal to 2.65. I claim that x1 is a better approximation compared to x0. How do I know this is actually true? You can find the value of the function at these 2 points. So I know f of 2.5 is minus 0.75. Same way I calculate f of 2.65. So you get the value 0.0225. So compared to minus 0.75, 0.0225 is closer to 0. So that's why I said x1 is a better approximation compared to x0. Still, I am far away from 0, right? I am not quite near 0. So I can do one more iteration, calculate x2, which is x1 minus f of x1 divided by f prime of x1. You find out the value, substitute in this equation. You get the new value 2.646. Quickly substitute in this function and see whether you are reaching 0. So f of 2.646, this will be 0.00131. So compared to f of x1, this is even closer to 0. So this is a much better approximation. Let's do one more iteration. Find out x3. You will find its value as 2.6457. And when you calculate f of 2.6457, you get something like minus 0.000271. This is not exactly 0, but this is very, very close to 0, right? So you can stop here, because even if you perform 100 iteration, you are not going to reach the exact value 0. You will get a value 0.00000000, then some value, right? So the idea is that you try to reach as close to 0 as possible, and if you are doing it using a computer, you can do a large number of iterations and improve your accuracy. But if you are doing it manually, especially in your exam, you can stop after 2 or 3 iterations. There is an assignment for you. Using Newton-Raphson method, find the root of the equation x e to the power x equal to 2. Correct to 2 decimal places. So first write f of x. F of x will be x e to the power x minus 2 equal to 0. You find f prime of x. Then you do a 2 or 3 iterations and check the accuracy. And if you're okay with the accuracy, you can stop there after 2 or 3 iterations. So that's an assignment for you. Before stopping, let's see how to perform this numerical method using Python platform. Now, for programming, I am going to take the same function x e to the power x minus 2 equal to 0. Since I have an exponential function here, I need to invoke the math module. So I start with from math import star. Then I define my function as f of x. So def f of x. Now this is x into e exponential x minus 2. I call it as y, then I return y. Now if you look at the equation, I also need to find the derivative, right? So I'm going to define derivative as fn of x. And what is the derivative of x e to the power x minus 2? Derivative of 2 is 0, so you need to bother only about derivative of the first term. This is going to be x e to the power x plus e to the power x, right? So I'm going to define it as y1 equal to x into exponential x plus exponential x, then I return y1. So f of x, f prime of x, both are defined. Now I need my initial guess, so I ask the user to input the initial guess. I input it as a float number. Now I need to perform the iteration. Now how do I determine the number of iteration? I know that when I reach the exact solution, f of x will be equal to 0. And if my solution is very, very good, then it will be very close to 0. Like you have seen in this problem, as you increase the number of iteration, your value will be more and more close to 0, right? So this is what I am going to do to set the number of iteration. So I will invoke a while loop, then I say ABS f of x. ABS f of x means the absolute value of f of x. This is important because if you look here, in some iteration f of x is positive, in some other iteration f of x is negative, right? So I want to get rid of the sign and focus only on the magnitude. Okay. So actually one more bracket is required here. This is a typo. Let me correct it. Okay. So the bracket is added. When I say the absolute value of f of x is greater than 0.00001, So what's the meaning of it? So as long as f of x is less than 0.00001, I keep repeating the iteration. Moment the value of f of x is less than that particular value, then I stop. So I can use the accuracy level to set the number of iterations. So moment f of x is less than 0.000001, I stop the number of iterations. And inside the loop, I put my equation x equal to x minus f of x divided by f prime of x. So I start with my initial guess x, keep improving upon it, then I check whether this condition is met. Moment the accuracy level drops below this particular value, I stop my iteration. Then you can simply print the answer. Print root of the given equation is x. So this is a simple way of doing Newton-Raphson method of finding roots of algebraic equations. So we'll stop here. In the next class, we will see how to numerically find the solutions of differential equations. Thank you.